Okay, in this video we discuss polymer dynamics. I will present some different models that describe this dynamics. Okay, let's start with the simplest one, which is the Rouse model. The Rouse model is a model of beads and springs. Okay, beads or monomers. There are n plus 1 and they are connected by n springs, like illustrated here. The model is very simple. The monomers follow overdamped Langevin dynamics. And there is no excluded volume, there is no hydrodynamics. We'll discuss about these effects a bit later. Alright, so let's go straight to the equations describing these Langevin dynamics, and they are given here. There are equations describing bulk monomers. Here R of n is the position of a given monomer at place n, okay, and this given monomer is connected by two springs. Therefore, it feels an elastic force, two elastic forces on this side and on this side, and this is expressed in this way. K is the elastic constant. All right, so this stretching is, this elastic force. It depends on the coordinates of the monomer itself and of the two neighboring monomers. Okay, and this overdamped dynamics, so I normally have the friction coefficient on this side. I divide by gamma and I bring it on this side. Gamma is the friction coefficient per bead. All right, these are the bulk monomers. The end monomers, they are a bit special. They are connected only via one spring. Right, this is the monomer R0 and this would be the monomer R capital N, the last one of the chain, right? Then we have the random force here. This is between quotes, not really a force because I divide by gamma, so it's actually the right definition of G is the force divided by gamma, and that fulfill the usual correlation relations, right? So the product of forces at different time average is a delta function in t minus t prime, but here we are dealing with a three-dimensional model, so every g of n has also a label alpha or beta which identify the x, y or z component. Okay, so this relation tells me that these components are independent, and there is also a delta function correlation Kronecker and M telling that the random forces in different beads are independent from each other. So this is the relation. Okay, so perhaps the bit annoying factor here is that we have to deal with three different type of equations. Well, actually we can only work with one type of equation if we add two additional fictitious bead, which I one at the end, one end, and the other at the opposite end, and one I call it as positions R n plus 1. This is fictitious in the sense that I let it overlap with, so I will not, it's not a dynamic variable that can stretch and so on. These last beads are just overlapping. Okay, in this way, because these two springs that I'm adding are actually not stretched, I actually can work and I use only one type of equations also for this monomer 0 and monomer Rn, right, when I add these new variables. Okay, so let's do some simplification. The first of all is we are going to a continuum limit. So instead of using discrete variable small n, right, you realize that actually this one is a discrete second derivative, right? So in the continuous limit it becomes a derivative, second derivative of R with respect to the index n. Therefore our equations they become a bit simpler. Okay, and now the fact that I'm using this boundary condition, say, it imposes in the continuous limit to the derivative of R in 0 and in n to be equal to 0. Okay, right, so these are the equations that we want to deal with. Actually the equations I want to normally so we go now to normal modes. This is the definition of normal modes, and unfortunately I made a mistake here. This is not infinity, this should be a capital N. So the normal modes are some collective variable. Instead of working with this position of every individual monomer, I define this kind of combination. I integrate over these positions and I multiply this by the cosine of p n divided by n. So, okay, this for every p non-negative integer 0, 1, 2, I can define this normal mode, and I do the same transformation for the g. Okay, so I have now the x of p. Instead of having n label n, I have an integer label p. These are kind of Fourier transform. Okay, so they are related to the R. You go to these normal modes, or vice versa. Given these normal modes coordinates x naught and xp, I can go back to the monomer position coordinates. So it's a kind of a Fourier transform, and there is an inversion formula that allows me to go back and forth from one picture to the other. So what is nice of these normal modes, that is, I can write transforming these Langevin equations. I can write the equation of evolution, time evolution for these normal modes, and these normal modes are independent of each other. So I have a p 0, 1, 2, so I have an infinite set of equations, but every equations, that equation, the evolution for x of p depends only on x of p, right? So these normal modes are independent of each other. So by doing this transformation, I simplify the problem a lot. So I have to solve these independent equations, right? Now, if you do this, I don't show all the technical the details of this, but it's just a little bit of math. Okay, so first of all, you find some prefactors here that depends on p, on the index p, and these are given here. Okay, so there is this zeta of p is a kind of stiffness of friction, right? And this k of p, it's a kind of stiffness stiffness coefficient, right? Because we recognize here these are equations of overdamped harmonic oscillators. We have already solved these equations, so right now we have written these things in this way. We don't have to do anything, just to go back and see the solutions that we had obtained for overdamped harmonic oscillators and just apply it to our case, right? Okay, so let's discuss a little bit more here. So if you see the stiffness of the normal mode, so this like the spring constant of the normal mode p scales as p squared. So the normal mode 0, for instance, has no so for k of 0 is 0. So for the normal mode 0, actually in this the differential equation here is simplified. This term is not there, right? It's just the mode 0 is just describing free Brownian motion. All right. The modes p equal to 1, p equal to 2, and so on, they have an increasing, while when p is increases, the k of p is also increasing, right? So it means that this elastic, this stiffness constant becomes higher and higher as you go higher in the modes. Okay, all right. And the final remark is that the original equation contained this stiffness of the springs in the Rouse model. Okay, I can change notation using equipartition. I know that that k multiplied by the average stretching of the springs squared is 3 times kbt, so therefore I can get rid of this k in favor of kbt and a, right? So it's the same. Okay, all right. So I normally use this final notation. All right. So this is our starting point, and now we can solve this equation. So before solving a few cases, let's recall that here, what I have here, if I look at this, and if you recall the overdamped harmonic oscillator, this quantity, namely this zeta of p divided by k of p, is a relaxation time, right? We have seen in the Langevin equation of overdamped harmonic oscillator, there we had k divided by gamma, right? So this is a relaxation time. So this is done in the next slide. Is relaxation time zeta of p divided by k over p. For p larger than 0, we can only because p equal to 0 we have already seen it's a special case, right? So for p larger than 0 I can write it out completely. So I have a quantity that divided by p squared, and this quantity I call it TR, which is the Rouse time, or also the relaxation time, or in other words the longest relaxation time, because you know, every mode has a different relaxation time. Okay, so the mode p equal to 1 has a relaxation time precisely equal to tau of r. The mode p equal to 2 has tau r divided by 4, and the next one tau r divided by 9, and so forth. Okay, so you see there is an infinite number of relaxation times. There is an infinite amount of mode. Each one relaxes with a different time, and there is one of these times is the longest, right? So these modes with p equal to 1 is the one that survives at the longest, at the slowest relaxation, right? So now we have said everything, and now we can go and discuss a few cases. Okay, so let's start with p equal to 0. I said it's the simplest case. Okay, once again I apologize. There should be here a capital N here instead of infinity, so the integral goes up to capital N. So what is the definition of x naught, right? What is the mode where with p equal to 0? Well, we recognize here this is just the definition of a center of mass, right? I'm integrating over all positions divided by the number of monomers. This is the center of mass, right? So we can identify this is a precise significance of this mode x naught of 0. And we have seen in the previous equation that this mode follows the free Brownian motion, okay? And the friction coefficient is this zeta naught we have shown in the previous slides is n times gamma. Okay, so therefore it's very simple. So this center of mass follows just free Brownian motion, and this is characterized by a diffusion coefficient, which is just obtained by the Einstein relation, okay, which is kBt divided by the friction. So n gamma is the friction, and this is the relation, right? I can rewrite this also in a different way, okay, and in the following form. So if I use the definition of tau of r, which is here, okay, so you see it's dependent on gamma on n squared. So I rearrange it and have it in this way, okay. So which is also convenient way for later, okay. So what happens here? Okay, so we start with our polymer at time t equal to 0 as a certain conformation, right? We have the initial position of the center of mass. It's it's a vector. I just write it for simplicity just x here, but it will be a vector r, center of mass. Okay, and the polymer moves. Okay, so it changes conformation, and the center of mass we have found that it follows like a free diffusion, right? The polymer is changing conformation, and the center of mass at a later time it will be found somewhere. So this red line would be some kind of hypothetical trajectory of the center of mass that follows some free diffusion. All right. So what do we know about this polymer? This polymer is an ideal polymer, therefore it's in equilibrium. The equilibrium radius of gyration of the polymer is as follows this ideal polymer statistics. So Rg squared scales as Na squared. Okay, but this Na squared is precisely what we find here in this expression of the diffusion coefficient, right? Okay. Therefore, if we now work out this and we take the tau r on the other side, right, and well, let's forget about this numerical prefactor. Now we're interested only on the scaling behavior, right, not on the prefactor. So what do we find? That the longest relaxation time, right, multiplied by the diffusion coefficient, this is the typical distance explored square distance explored by the center of mass after time t of r, this is just diffusion, right? So we find that that this t of r is also the time needed for the center of mass to diffuse of a distance at the distance rg of the order rg. Okay, so we see that our polymer. So this, what is the idea of this relaxation time? The relaxation time is the time such that the polymer has lost memory of its initial configuration, right? If I would make a movie of this polymer and I would make pictures of it, you would be able to connect this picture if you see a few snapshots to say, okay, this is the polymer is evolving in time, is changing it a little bit, it's relaxing some part of it, but you know, in a certain specific way, and you know, as the movie goes on, the polymer has lost, you know, is less and less correlated to its initial. Sorry, let's go back. Less and less correlated to this to its initial conformation, right? And here, this relation tells us that this relaxation during this relaxation time, well, it's also the time at which the polymer actually has shifted, and the center of mass has shifted and gone outside of one radius of gyration. So if it's outside one radius of gyration, right, it must be a totally refreshed conformation. And this is what this relation, and this is a useful relation because we can generalize a bit later for other problems. Okay, another quantity we want to discuss is the end-to-end distance. All right, so the end-to-end distance vector is the difference of position vector of the monomer 0 to the monomer end-to-end endpoints, right? And it turns out that if we use the relation that was given in the previous slides, right, the relation connecting the monomer positions to the, you know, normal coordinates, we can write this end-to-end distance as follows. You know, it's a very simple calculation, say, as follows, as a sum over normal coordinates. Actually, it's a very simple, and it turns out that if you work out the capital N and n equal to 0, here you get just a sum over odd p's, odd normal coordinates. So it's p is equal to 1, p is equal to 3, 5, 7, and so on. Okay, so this is now that we have this this result, we can calculate the correlation between end distances. So we calculate the end distance at time t equal to 0 and the end distance at the time t equal to t. We make take the scalar product of the two. We make the average, and we want to know what is this quantity. Now, thanks to this this relation that we can express this quantity in normal modes, the calculation becomes very simple. Why? Because we know that normal modes are for p equal 1, 3, and so on. They are, you know, they describe, well, they follow the dynamic of an overdamped harmonic oscillator. So we have already calculated for overdamped harmonic oscillator that the correlations of oscillators' positions in time is just given by this quantity. This was done already in the previous lectures, right? You have just to transform the variables in the right way, and remember that this is a 3D problem now. Okay, so this was already known. Okay, and now we can use this result, right? So we substitute, instead of r of t, we take this expression with t, and instead of r of 0, we take this expression with t equal to 0. So this this correlator is inside this when we take this product, right? And also, you know, when you take the scalar product of this with the other sum at t equal to 0, we know that modes with different p's evolves independently. Therefore, the scalar product of x of, say, p of t and x of p prime of t different than p, these kind of correlators with p and p prime different are 0. So only the diagonal terms survive, and just this is the result, right? So minus 4 squared gives 16, and then the correlators and here are giving this result and are putting back here. We can also rewrite this result in this form. Okay, so the end distance decays in time in the following way. It's an infinite sum of exponentials, right? And if we now set the time t equal to 0, right? So what we get here is r squared, right? R squared. We set the time t equal to 0. This part, the exponential, becomes equal to 1. Okay. So summing over p odd 1 over p squared, there is this exact result. You may not know it, but this is true. Okay. The sum of this is pi squared divided by 8, right? So it means that I can easily calculate this, pi squared divided by 8. So what is left here on this calculation set, when I calculate r squared not equal time, so the previous correlator equal time equal to 0, I get na squared. But this is precisely the equilibrium end-to-end distance, right? We have seen in the first lectures that polymers in equilibrium, ideal polymers in equilibrium, the end-to-end distance is just n times n squared. So we find it back here. But this result actually is it contains all the time evolution of this quantity. In particular, okay, this is a sum of exponentials, right? But if I go to sufficiently long time, you see that there is time, this p sum over p odd, there is p equal to 1, there is p equal to 3, and this gives minus 9t, and there is p equal to 5, 25, and so on and so on. So as soon as you go to large p, you see that this decays faster and faster in time, right? And for sufficiently long time, there is an asymptotic behavior. So of all these exponential, only the one which is decaying the slowest survives, and this corresponds to the mode where p is equal to 1. Okay, and this gives this type of exponential. Okay, so the long time behavior of this end-to-end distance relaxation is just a simple exponential, right? Okay, so you see for harmonic oscillators we also found a simple exponential decay, right? But this, in general, this one is an infinite sum of different relaxation times, of which at long time only the slowest mode survives, the one that decays the slowest survives. And this result is given here. All right, so this is a final picture. It's a kind of a recapitulation of what we have seen. We have a vector at certain polymer configuration at time t equal to 0, and our end distance is, for instance, this vector r naught, and the polymer moves and evolves in time. The endpoints are shifting after some time, t larger than 0, the endpoints will have changed, and we have a vector here. I forgot to put the sign of a vector here. We have a vector r pointing this way, and so you see that we are here in these calculations, we are averaging over all possibilities of after some time t, where these over all possible realizations where this vector rt will be, right? And if you wait long enough, for instance, these two endpoints can even swap, and rt can points mostly downwards, and at that point you know that your polymer has lost correlation of this initial orientation, and also, okay, yes, in the course of time this will decay, and this is the mathematics. It's nice. It's an exact result at long time behavior. All right. Okay, this is all for the end distance dynamics, and now we are looking at the dynamics of a single monomer, right? In the previous case, the end-to-end distance is, the two endpoints, but let's look at the mean square displacement, and for simplicity, Here I want to consider the monomer with n equal to 0. I do that because the expression is a bit simpler, but the same physics also holds for any other monomer, right? And what you have to do, sorry if this is appearing, so what you have to do here is to do exactly the same that we did before. Write this in terms of normal modes, so take the expression of the previous slides, and again here, and take subtract the two, right, at two different time, and squared, and then remember that different normal modes that don't talk to each other, so they don't contribute to the correlator. So so you have one contribution here that comes from normal mode p equal to 0 if you do the whole calculations, and one other contribution that comes from modes p larger than 0. Okay, this is what you do. If you repeat, you use the same strategy as done in the previous slide. Okay, right. Now I don't discuss the two, but I already recognize here that this is the diffusion of the center of mass, right? This is the mean square displacement, and of course it will have it will displace with the center of mass part of it, but also it has another contribution that comes from modes p larger than 0. Okay, and I don't do the analysis of this. There is a bit of mathematics that you have to do, and to work out this sum and to prove what actually that you can do different type of expansions here according to whether the time that you're considering t, which is a variable here, it's much smaller than the slowest relaxation time that we call the Rouse time here, or is much larger than the longest relaxation time. So if it's much smaller than the longest relaxation time, you can do a certain type of expansion, and you see that the dominant contribution to the sum actually comes from this first part, and this scale as a square root of time. Okay, so this is the scaling behavior. Whereas if you go to very large time, you find that this one is gives the dominating contribution, and this is linear in time. Okay, so for a mean square displacement of a quantity that is performing diffusive behavior, we expect you have a squared here, and we know that it goes linearly in time typically for ordinary diffusion. So the fact that what we find here, and this is why I emphasize with this frame, is that it's kind of an anomalous behavior. The short time is an anomalous behavior, shows an anomalous behavior that goes as the square root of time instead of going linearly with the time as expected. That's why we call it this anomalous dynamics. All right. This anomalous dynamics, how do we understand it? Okay. So now we have said here that we are discussing the monomer n equal to 0. Okay. I indicate that a tagged monomer here, well, normally we are discussing the monomer and the monomer here dynamics, but I told you that the expressions are very similar for any monomer. So let me take one monomer here. So what you're measuring here, the mean square displacement, you could do in an experiment as follows, right? Suppose that you can label this monomer, which means put some fluorescence molecule, for instance, fluorescent molecule that gives you a signal that you can see. You see where this molecule is, and you measure how this moves around, the mean square displacement of this monomer. Okay, so what you find is that at short times it scales as a square root, and at long time your signal, your mean square displacement, scale as ordinary diffusion. And why does it scale as a square root of time at short times? Is because this is not really a free diffusion. So at short times, actually, at short times the monomer feels the presence of neighboring monomers, strongly feels the presence in the following sense. If it moves at short times and it's going this way, it's stretching one spring, which is here, okay, and compressing perhaps the other springs on here, and then you know that by doing that the monomer is not really doing free diffusion, is actually strongly constrained by the neighboring monomers at short times, and that's why the mean square displacement grows more slowly than just free diffusion, and this is the square root of t. This is the anomalous behavior. But finally, at sufficiently long times, what happens at long times is the whole polymer also moves, right? And the center of mass moves, right? So this mean square displacement at long time, it gets dominated by this center of mass terms, okay? So it's that's why you have two regimes. It's very interesting, this expression. We find some anomalous behavior at short times, but when I mean a short time, you remember that this aroused, the relaxation time, scales as the length of the polymer squared, right? So it can be substantially, well, it can be a strong effect if the polymer is sufficiently long, right? All right, so we have seen three quantities that we can fully analyze with the Rouse model, and it's very nice. The Rouse model is analytically solvable, so we can calculate plenty of things, of properties, right? But of course, it's very ideal as a model. And for instance, the Rouse model that we have just seen neglects excluded volume interactions. It allows the monomers to overlap, which is kind of unrealistic, as we know that real polymers, they have excluded volume and so on, of course. And so we can think about, well, so what do we expect when we have a real polymer and not an ideal polymer? So what happens for the diffusion of for instance, the center of mass? We will have Einstein relation also in this case, right? KBT divided by the total friction, right? Even if we have excluded volume, right, the total friction will always be the additive, so like the number of monomers times the friction per monomer. Okay, so that's why for excluded, even in the case of excluded volume interaction, we expect that the diffusion coefficient will still scale in the same way as the ideal Rouse model. What changes, right, for the case of an excluded volume interactions is that the radius of gyration of our polymer will scale not as an ideal polymer with the square root of n, but with a law which is n to the power nu, right? The Flory exponent. You remember this 3/5. Okay, so this is definitely there. This excluded volume gives, well, the real polymer is more swollen than an ideal one. Okay, therefore, we can combine these two information to calculate again the Rouse time using the same type of reasoning that we said before. The Rouse time, the characteristic time at which the polymer exceeds, so moves to a distance of the order of the gyration, the radius of gyration, right? Now the radius of gyration squared brings an exponent n to the power 2 nu, and the diffusion coefficient brings factor 1. Okay, so for ideal polymer in the Rouse case, this relaxation time is n squared because nu is 1/2 for ideal polymer, and now for a polymer with excluded volume we have this new scaling law, right? So this is the first case. Another case that we want to discuss, and it's an interesting situation, is the effect of hydrodynamics. Okay, what is hydrodynamics? So we are studying single polymers here in a certain, these polymers will not float in vacuum, right? It will be immersed in a fluid, right? When it is immersed in a fluid, there is a kind of there is a back reaction of the fluid. You know, if the monomer moves one monomer in a certain direction, it will perturb the fluid, surrounding fluid, and the fluid will be set into motion, right? So there will be some velocity field that propagates. The fluid is like water, and the fluids that we are considering are incompressible, right? So there will be some motion actually up to infinity in principle. There will be some velocity fields, right? And this, what this picture shows, is this back reaction. So one monomer moving in some directions and bringing with its motion piece part of fluids, and this part of fluid setting other monomers into motion, right? So there is actually not only in this when we have hydrodynamics, not only spring interactions, but the motion of one monomer here can influence the motion, can influence the, you know, can influence the motion of the of another monomer which is far away, right? Okay, so of course this is much more complicated than the Rouse model, and there are different ways of taking this into account. We will use a simple scaling arguments. So what do we know about this hydrodynamics of motion of you know, objects in fluids? Well, there is a very celebrated relation, which is the Stokes force. So Stokes consider a particle, a spherical particle actually, of radius r, immersed in a solvent, and the solvent has a certain viscosity, eta, all right? And Stokes derived that the force, the drag force exerted on a particle, if the particle has a certain velocity v, okay, the drag force is minus 6 pi r times eta, all right? So this is this 6 pi r eta is the friction coefficient, the friction felt by the force, by the particle, you know, due to the presence of the fluid. All right. Now, okay. So, all right. So, if we think that our polymer, the whole polymer, no, I'm not talking about a single monomer, but the whole polymer, we can picture the polymer as some kind of a sphere, spherical object of radius, the gyration radius, right? We can use the Stokes formula to deduce the friction to the hydrodynamics that is due to the resistance of the fluid of the whole polymer. And this will be given by 6 pi eta. And now instead of r, that was the particle radius, I use the radius of gyration of my whole polymer. And this scales as a n to the power nu, right? So given the friction of the whole polymer, I can write now that the center of mass diffusion, you know, by Einstein relation would be kBt divided by the total friction. And now this total friction I calculated using this Stokes formula. Therefore, I find that the center of mass, you know, and if I look and I'm focused on the n dependence, diffuses with a law which is scales as n to the power minus nu, right? Or 1 to the n nu. Now, again, I use a similar relation that is here above to deduce the relaxation time. Actually, I put an equal, I should have put a quasi-equality sign. This is just a scaling relation that we are. And again, the same reasoning, radius of gyration squared, diffusion of center of mass. The radius of gyration squared does not depend on the dynamics, is an equilibrium property. Therefore, it's here, from this I get r, so I have this relation, right, is n to the power 2 nu, that comes from here, and from here there is a factor 1 n to the power nu. So okay, so this relaxation time is now n to the power 3 nu. So you see we have a different type of relaxation time behavior when we have hydrodynamics. Okay, so now we can compare the two. So okay, the Rouse model with or without excluded volume interactions. the center of mass scale diffusion scales as 1 over n. Of course, when n becomes larger and larger, the diffusion constant becomes smaller and smaller. You know that the polymer is longer and longer. It's more difficult to set in that it's, you know, this diffusion constant goes down, so it has smaller excursions, whereas and it's also here. It's also the case here. So it's a decreasing function of n as n increases, and the relaxation time increases with n because to relax a longer and longer polymer one needs more time. Okay, and here it increases as 1 plus 2 nu here and to the 3 nu. Okay, so there is a more rigorous way to obtain these results, a more precise way, and but you know, we discussed this ZIM model just from using scaling limits, scaling relations of this kind. All right, but already these very simple relations that are you know, defined in this way are actually seen in the experiment. So if one take a solution, and I call this diluted polymer solutions, right? What does it mean? It means that I have a solvent and I have a few polymers in my solvent, but the concentration of these polymers is such that the average distance between two polymers is very large compared to their gyration radius, so actually they do not interact with each other. You can say an ideal gas of polymers in a liquid, right? And people have done experiments and they can measure the diffusion coefficients of the polymers as a function of the molar mass of the polymer. The molar mass is proportional to the length of the polymer. Right? So the ZIM model with hydrodynamics predicts, as we have seen, that this diffusion coefficient of the center of mass of the diffusion of you know, of the polymer scales as 1 over n to the power nu. And actually this law is very very well verified in experiments, right? It's you know, you see two lines. If you were to plot the line for the Rouse model is 1 over n, it would be much steeper than these two. All right, this is n to the minus 0.6. This is the Flory exponent that we expect in this case, right? And we see it. We see that the Rouse model doesn't work, but the ZIM model works. Okay, right. This is about diluted polymer. So if we now go to a more concentrated polymer solution, which is the case of polymer melts. What are polymer melts? Polymer melts are dense solutions containing polymers. They can even be made only by polymers. They can have a little bit of solvent also, but let's say that these polymers do not stick into each other, so the system is still fluid. The polymers can flow through each other. And let's also consider that the length of each polymer is not too large. So if in that case, and one finds that actually the Rouse model works. You know, experimentally one finds you know, the diffusion coefficients or relaxation times as expected from the Rouse model. And in this case, actually, there are so many polymers that hydrodynamic interactions are screened by the presence of all other polymers, and one can argue that, you know, that the correct model in that case is the Rouse model, right? And the Rouse behavior is found in this type of polymer melts. Okay. So if now the length of the polymers is very long, so if we consider a polymer melt, you know, with very long polymers, so what happens? You know, the system is described yet but another type of dynamics, right? It's not the Rouse model anymore. And what happens is that actually, if I look at one polymer that let's draw it in, it's shown in red here, right? It's nothing special of this polymer. I'm just focusing on one of the many, but I could take any of these. You know, effectively, all the other polymers are so they are entangled to it, right, in such a way that this polymer has not much freedom to move on sideways, right? So it could shift a little bit here, but you see here there is an obstacle. So this one cannot go here. It's not like a free Rouse polymer. Here there is another polymer in the way and another polymer in the way. So actually this poor red polymer that wants to move, what is the option that this polymer has? It's only to slither away, so to perform a motion that we call reptation. It's like a reptile, you know, that it's like it's full of obstacles and so on. You can only sneak through them. You can't do sideways as our Rouse model was doing. Also, this model is actually a model of an effective 1D motion, slithering motion, that is similar to that of a reptile. Okay, and this construct that you see around the polymer is not. It's called a tube. It's not a physical object there, but it's a kind of indicates that our polymer is actually confined because of the presence of all the other polymers. It's confined in a small space. This is called reptation and this confinement. All right. So if we look at this polymer, okay, how can a polymer move away from these configurations and go and evolve and relax into a different one? Okay, so the only way is one-dimensional motion, diffusive motion here, which is called reptation. And to reptate, right, like a reptile, you need some stored length. So the reptile is not stretched. Right, like a snake is not stretched, but it's a little bit is compressing part of his body, like you see here. And I call this compression like a stored length. And this stored length can be transmitted and go upwards or downwards. Okay, here is a thermal motion, right? So it's random motion, so it can go sometimes upwards, sometimes downwards. Okay, so this is the reptation motion. So we need the stored length. All right. So, and now we want to do a very simple, again, scaling argument here to understand how the polymer relaxes in time. Okay. So what is the relaxation time of this polymer melt? What do I want to calculate? Is actually I would like to calculate the characteristic time. Well, to me, relaxation means that this red polymer has escaped, right, from its tube, and it has, until the polymer is inside the tube, its conformation will always have this type of characteristic S shape of this kind. It's only when it goes out of the tube that it enters into a new tube somewhere else, right, that the conformation, this new tube, will be uncorrelated with respect to this one. So how can a polymer escape? The red polymer can escape from the tube. It needs store length. It needs diffusion of store length, right? So let's suppose that there is no store length in between, that the polymer is somehow ideally stretched, right? There is no store length inside. The store length can form at one end of the polymer, so you can have a little bit of compression of length, and this length is, this compressed length is propagating a little bit, is diffusing up. Most of the time will get out from the same part, but sometimes it will manage to diffuse, and following back, and then coming out from the opposite side, from where it has formed. If it does that, right, what happens here? The polymer will be globally will have moved a little bit from this configuration. So this tube will longly survive, but this one will have moved and a little bit. And then there will be a net polymer of motion a little bit upward. Okay. So first of all, suppose that one store length defect forms here. The length of the polymer is of the order n. So for this stored length to diffuse along the backbone of the polymer of length of order n, you know that the diffusion time scales as n squared. This is the 1D diffusion, right, along this contour. But once this is done, we have moved, okay, only very little our tube out of our tube. One needs of the order of n of this stored length to leave actually the tube, right? So if we count now the power, we have 1n squared, this time needed for a given stored length to cross the tube, but we need n of this stored length to leave such that this red polymer leaves completely the tube. And if we count this power, we can n to the third. Okay, so first of all, prediction of the reptation theory is that the relaxation time should scale as a polymer length with n to the third. And if we go back, we look at the Zim and Rouse model, this reptation times is much longer, right? So it is n to the third versus n to the what is n squared for the Rouse model, and n to the power 3 nu for the Zim model, right? It's definitely scaling much higher, so the relaxation time becomes rapidly very large, and this is because the only way that this polymer has to renew, this melt has to renew his conformation is to perform this 1D motion, okay, and that's why you have this high power, right? The second thing is okay, we want to estimate the diffusion coefficient also. Right, what is the diffusion coefficient is to estimate the diffusion coefficient, we do the same scaling reasoning. First of all, we want to the end-to-end distance of a polymer of this the end-to-end distance of a tube, and for that, it looks a little bit weird. We use the ideal polymer statistics. So we say that the end-to-end distance, we claim the end-to-end distance scales as the square root of the length of the polymer. This is ideal polymer statistics, but this is not the statistics that we expect for excluded volume interactions. And here there are a lot of entanglement and overlap. But the point here is that why actually was Pierre-Gilles de Gennes, a Nobel Prize in Physics for, and one of the founder of this field of polymer physics that proposed this scaling law. What he said is that that the polymer actually here it has the same statistics as an ideal polymer without excluded volume interaction, because actually it's hardly interacting with itself via excluded volume. It interacts with many other polymers, but not with itself. Okay, so this is not self-avoidance. Okay, and it's still, and it turns out to be true and close to be true that this law is valid. Okay, and therefore we have now all the ingredients, because we use always the same scaling argument that we have used so far. So what is the diffusion coefficient? The diffusion coefficient is this r squared divided by the relaxation time. Okay, and now the r squared, ideal polymer, gives n, and the relaxation time we said is r cubed. So we find that the diffusion coefficient is 1 over n squared. So you see in this reptation theory, say if we stay this way, we can do the story a bit more complicated, make it a bit more complicated, but this is capturing the essence of this. And what is very nice is that if we look at experiments of polymer melts, where melts of very long polymers, where we enter in this regime of strong entanglement and this regime of reptation, we see that relaxation times and diffusion coefficients actually they behave actually very closely to these predictions. So the experiments are not spot on the power 3 and on the power 2, but they slightly deviate. Okay, experimentally, one typically finds relaxation time that scale is n to the power 3.3, and I guess that here it's instead of 2 is 2.1. Okay, so very close, but not yet fully overlapping. Actually, there is also a theory explaining these deviations, and I will not enter into the detail. Okay, but despite these very small differences, it's a quite strong and successful theory, and you see we are discussing here a strongly interacting system, but via this scaling argument one can understand quite a bit. So I have some general understanding of what's going on in this system.